Good morning, everybody. I'm Roberto ARAYA from Chile, and I am going to share with you some thoughts about why and how to teach AI and computational thinking in our schools. Um, so, first, why? Um, think about this following situation. I have my app here, small app, and this knows where I am right now. If I move, knows where I'm moving. If I want to go buy something, probably it knows that because I have searched on the internet before. And the app also have read what I have shot recently. The app also have heard and recorded and analyzed what I have talked with my mother, with my daughter, and have it so a pretty good idea what's going on with me today, yesterday, the last weeks, month. Probably knows my uh, personality, if I'm open, if I'm conscientiousness, if I'm neurotic. Also, probably knows my mental health right now, if I'm depressed or not. So knows a lot of things about me. He's analyzing all this pattern, and maybe it can make me suggestions. So that's AI. That's the computational thinking behind this small machine. But not only suggestions, maybe I can also make decisions for me. And maybe talk with other apps that also use AI and make decisions like driving my car, maybe giving me some pills, drugs that I need. So this is completely different what we have done up to recently. It's a completely new world, having enormous impact on all of us. So we are in the world of smart autonomous agents. They analyze the data, what we are talking, our what we have been writing, uh, whom we communicate with, and so knows a lot about us. And they're autonomous. Maybe they can make decisions for us. So it's very important for the citizen to know what is really going on and to understand this technology. And so this is very important that we start doing um, working with this technology, understanding this technology, and teaching it in our schools. So the idea is computational thinking. All behind this is computation. It's a machine that does all of that. At the end, it's just one and zeros. But no, this is about the very end. So we have thought that these are basically three big pillars of computational thinking that I'm going to talk today, and we should teach to all our students. One is algorithmic thinking. That's a classical way to think about computers. And the computer follow procedures, very precise procedures. So you have to give very precise instructions and will follow these instructions. So the whole thing is how to give to this computer all these instructions. And there's an algorithm like the algorithm for doing addition or multiplication. That's very precise instructions. So we have been doing this for a long time, but now with the power of computer, we can put more and more algorithm and with much more power. The second is modeling, it's computational modeling, to understand the world with computers. We need computer to understand weather, to understand the climate, to understand the genetics, to understand epidemiology, how this virus spreads. We need to understand how is this done with computers. So how we model, how we can put this world or part of this world on the computer and be able to predict what's going to happen under different circumstances. And if we do this control or this other strategy of control. And third is machine learning. Machine learning is making the computer not only following instructions, not only capturing part of the world, making predictions, but the machine learning by itself. So this discovering patterns, and then that will help making better decisions. Learning, for example, to recognize a face from other objects, or who is the person in that face, and also mental health of this person based on this videos of the person, understanding words and making sense of what is going on in a talk. For example, in a lesson that is being taught by the teacher, try to summarize the lesson automatically and be able to then highlights the main points and also highlights the main pedagogical strategies just from listening and watching the teacher. So let's start first with algorithmic thinking. What is algorithmic thinking? Just here is something that we can illustrate this. This is like from a coloring book we have designed for first graders. Says paint the dress green. So the kid is just starting to read. I have to read this and then select the color and paint green. So it's just reading instruction and following that precise instruction. The second instruction is more complex. In each box, paint at least two blue balls. So you have to go to each one of these boxes. In each box, at least two has to be blue. So you have like what is called in logic, it's quantifier. For each box, do something, and the something has at least, so it's two quantifiers. And kids like this, it's like they're a computer, has to follow instruction, but now in the next one, here they have to write instructions. So send this to a classmate, write instructions, like paint the dress green instead of that, another instruction. And with these boxes and balls, another instruction. For example, in each box, paint more blue balls than red balls, for example. So that's way, it's a strategy to teach programming and algorithmic thinking to students. Here's another one. So here is, where is my purse? And so the kid have to read, can you find it? It's under a box, under a book, sorry. Not up of the tree. It's not at home. It's near the duck. So you have to read all this information and then find it where it is. And so this is also for first and second graders. So it's a search with some information. And here in the next one, they have to write the instructions. So you have to write instructions so a classmate will find something that is hidden. So it's reading means understanding instruction and following it, and then the other one is coding, writing instructions. So it's algorithmic thinking. We have a whole set of, activities in a coloring book. It's a coloring book we have for kids, and they start with very simple instructions and to more and more complex, more logical sophistication. But also I have one for reading and following the instructions, another one for writing instructions, so a classmate will follow those instructions. Then comes modeling. Modeling is very important to understand the world and then to solve problems and control somehow the world. Means you are able to synthesize or characterize the world in a simplified manner, capturing the essential thing. So I'm going to show some examples. For example, in forest fires. Forest fires, you can imagine the world as this board, just a board. So instead of having a very rich landscape just above, with each of these cells could be different colors, but you will see that here you have this a cell that is on fire now, this red one. So how will it spread? For example, you can have rules like this at the left. If the cell was red or black, then cell is black. So next time this red cell is going to be next time it's going to be black. And if a neighbor's cell was red, then the cell is red. So this is spreading of the fire. Else will continue to be white. For example, the next time this will be like this one. So the red was black and the neighborhood will get red. So you can see here that we have modeled the whole landscape in the region of the country with a simple board. And in each cell, you have a propagation rule. If it's red, next time it's black, but the neighborhood will spread and will get red where fire is there. And so what will be the next one then? Can you predict with this rule? And for example, now consider the following situation. You have two sources of fire. And so what will be the next one? And how could you protect this? For example, if I would make a planning fire here, and you have all this black, then this would be a way so the fire would not spread. It's like it will be a barrier for the fire. So how would it spread in this case? Yeah, well, so this is an example of modeling the world for forest fires. All software for forest fire make predictions based in this very simple idea. Yeah, with you can add more complexity because not all part of the board are the same. It depends on the kind of plants or trees they're there. Also depends on the wind. Also depends on slope, different part of the landscape. So you can add more complexity, but you can see here that we have built a computer model of a real life, very important phenomena that will help us to control these cage fires. Another example is segregation. This is a very popular example. How do people segregate in different groups? So here we have again the world landscape. Each one will be a house, and there are blue people and red people. White spaces means are empty. Now imagine that you have the following rule. At each time you select a cell, and if around his neighborhood, the neighborhood is, for example, for this one, neighborhood is red, 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 empty, blue, blue, white. So there are more red, 1, 2, 3, 4 red, and only 2 blue. In this case, this was the rule, then this person will move to any other place that is empty at random. If you do this and everybody do this, after a while you get this. And you see now there are blocks of blue people, blocks of red people. And so you continue doing this, you get to this. So clearly it's a red area, yeah, another red area, blue areas, and you have the city completely segregated. So a very simple model explains how segregation is produced. Basically, because people doesn't want to live being a minority in his neighborhood. So want to move any other place if you are surrounded by people different from you. This is a classical model, and Schelling got Nobel Prize in economics in part for this model. Here's another one for coronavirus. You have these balls that represent, it's a model represent people, and you have 3 people here, and these are then 3 people here and 3 people here. So the same number of people in this place, but here larger balls mean they're not using masks, so they can spread virus. Uh, if someone get up to this, then we have probably a contagion. So this is with normal masks, and this is with very very good mask. So you have to be very, very close in order to have contagion. So this is a model of how, for epidemiology, how people produce a contagion. Also, they can move. So mobility is important. If you move, then there's more possibility of a collision, like here. For example, this compared to this is moving much quicker in a given amount of time. It moves from here to there, but this is only from here to here. So if you have more velocity, more motion, more mobility, more possibility of collisions there are, and more possibility then of contagious. Here is more people moving, so this orange one could be hit by one of these. Here you have more people, and so the contagious phenomena depends on the number of people. The more you have, more possibility of a collision, means possibility of contagion. If you move more quickly, you have per unit time more possibility of collision as well. And if you have bigger balls, it means no mass, more possibility of collision between the balls, means more possibility of contagion of the coronavirus. So you can see here is this very simple model. Is you can see, and you can do this in small table with these balls and count collisions as it is where it's as a model of the contagious process. And then you can write for this. This is the velocity, and this is the time, and you have this, and then you have the possibility of collisions. So you can build a computational model of the propagation of the disease and the different conditions depending on the density of populations, how many balls, according to the mobility, how much do they move each person, and according to the size of the ball means using mask or not using mask. So we have seen modeling, now machine learning. Machine learning is an area different because it's not about programming, not about coding, but it's about training. You train the computer similar as you train your dog. So you don't give a precise instruction, just give examples what will happen on different cases. So it's a completely different paradigm, but has profound implication because one, machine learning applications are growing very, very, very fast. Second, as we talked initially, agents are learning automatically in this way. So they're learning from examples as training. Sometimes explicit training, you teach a computer, sometimes it's learning from you. from what you talk to others. So maybe you don't know, but machine is learning from you and from others. And so it's completely different paradigm and have profound ethical and legal consequence. For example, the machine is learning what to do automatically from what you've been doing before. But maybe in some situations could be very harmful for you or for other people. So it's very complex because machine maybe could get a pattern that's better than the pattern you have already gotten. In general, it would be better, but in this specific situation, could be, something very with big consequences you have to think about more carefully. And so this is an area that is very important. Our citizens know the technology behind how is this working and the implications. So here's an example, very simple example we've done in schools for elementary schools. You see this pond with fishes. Some of them has blue eyes, other red eyes. So is there any pattern? Do you have any ideas what pattern is there? Why some of them are blue, some of them are red? Okay. Here is another pond. So it's the same pattern. Now try to guess here which of them has blue eyes, which has red eyes. So the kids have to do this, try to find the patterns and then make a prediction. So this is a very interesting thing that the previous 2 ponds to the kids is this is called for training. Several examples for training, and so you don't giving to them any instruction how to paint them. So they have to find the pattern and then you apply here to paint the eyes of the fishes. So you had the idea of training and then applying to make predictions. So that's what you have to do. Now this is, for example, the solution. And then once when you make a prediction, you compare it with what's really the color that was behind. And this is called a test set. Initially you have a training set. Now you have a test set and you compare predictions, how your model is in this new situation. This is basically the heart of machine learning. A training set to train, and then a test set where you test your prediction that you have learned from the training set. Here's another one. The block A are people, and some of them have a red, here they have a red painted in the front head. This means they are sick. For example, they have coronavirus, for example. They are infected. The other ones are not. So can you, from the test set A, devise a pattern? And if you have the pattern, can you apply in B? And in B, we have the solution. So after you apply the pattern in B, we can see how accurate was your prediction. For example, the first 2 here in A is a man, a lady. This doesn't have anyone. This either. For example, you can see maybe these are younger than this one. So the old people tend to have the red one. They're infected. Yeah. Again here, old man. What is this middle age, like this one? Yeah. This is old lady, also infected. So the pattern is not perfect, but there's some kind of a pattern because if you compare, it's not perfect because if you compare this man with this man look alike, but one is infected, the other is not infected. And then you have to, once you have this pattern, apply here. So you have a training set where you learn from this set, and then you have a validation set or test set where you make predictions, and then you can compute how accurate you were with the predictions. That's the basic paradigm of training. That is completely different from writing or giving instructions and following instructions. Here there is no instructions. It's just training set, and the machine, same as you, will find a pattern and then make predictions according to this pattern the machine has found. One practical example, another practical example, this is oil analysis in big mining trucks. So here we have 16 cases. Each one is a truck that has concentrations of iron, copper, and sodium in the oil, flash point, and diagnosis. The flash point is the point where the oil starts to boil. And diagnosis machine was normal. The first one was normal. And all these are normal. And here it has water contamination. So the idea is, what is the difference between water contamination and normal machines, engines? These are engines. Can you predict from the oil, just go in these concentrations, iron, copper, and sodium plus flash point, this temperature? Can you predict which is normal, which has water contamination into the engine? Well, if you plot sodium and flash point, and black are the water contamination, and the ones white balls are normal, maybe you can see that when the sodium is high, you have more black. When the sodium is low, then you don't have water contamination in the engine. So you can see the pattern here. So once you plot the information in this way. Here you can see there is a threshold in sodium concentration that allows you to make the prediction. So you have it in our database. So initially we have 9 engines normal and 7 with water contamination. When the sodium is less than 17, all of them are normal. When the sodium is higher than 17 particles per million, then all would have a water contamination. So this is a case that we train a computer with this 16 cases, and the machine will learn to find this threshold, and we learn that the sodium, the most critical one for that. And now we did it by hand, doing some graph analysis and plotting, but the machine will have to learn this by itself. Doesn't have eyes like us, but it can be all these reduced computations as well, and the machine will find this pattern. We'll learn this way. Here's another application in virology with the COVID. This was an coronavirus, 814 deaths up to 8th of February. And from at that date, it was a publication from the Journal of Virology, and you have 17 first cases in Wuhan, China, 17 cases. Each one is first is a male, 61 years old, had fever, comorbidity, has comorbidity, surgery, not information not available. First system to death, 20 days. So in each case, we have how many days the person had death, how many days to death from first symptom. And these are the 17 first cases documented of people that ill and then they died. And so the question is, one of them is, the question is, one question will be who will die, will not die, or who will be severe or not severe. I mean, how fast you will die or not will die. It's a different question. And looking at the data, we found that Those with age higher than 69 will die much, much higher. The machine will learn automatically, and you can do also a simple graph to devise that pattern. So 69 years old makes a big difference. Who older than 69 will die much faster than the younger ones. And a way to do this is you put here the number line with the ages from 40 years old to 90 here. Each one of these is a person that comes from the previous list. The circles is person that it takes longer to die, longer than the median. And the crosses like this are the person who took less time to die, or they die very fast. And you see that here at the right there are more crosses, means above like 69, much more crosses. Means above 69 years old, people die faster. And below 69, they died slower. But it's not completely clear cut. And that's in most typical cases, that's what happens. You don't have exact separation. So the 69 is a good threshold to think the machine will devise with this threshold. AI in education. I think I would like to show also this can be applied in education. For example, here's a teacher, what a teacher is teaching. In the smartphone is recording, and from the recording is making transcription. What it's saying is all this in the cloud. We have been doing this automatic transcription of what the teacher is saying. And from what it's saying, you can see certain patterns. These are different. These dots are different classes of different levels, and this is more contents and science skills, or here is more content math skills and science skills and math skills. So each of these is somehow the computer, once the teacher finished his class, analyze his talk, the transcription of his talk, we realize if his class is more focused on skills, science, math, or contents. So it's just automatically. We have done different analysis. Here is this is just the same thing, but just for one class. Every 5 minutes, how is the trajectory of the class in terms of skills, math and science, and content? So somehow the whole class, this is 60 minutes class, is like trajectory in this space. We have done several analyses like this. I recommend you this Springer book recently, Methodologies and Intelligent System for Technology Enhanced Learning, 10th International Conference. We have 3 papers there in our group. One of them written together with the people from University of Jyväskylä in Finland. We analyze discussion between students automatically, the voice of them, speech recognition, transcription, and try to, in science class, to detect the phase of the discussion, the analysis. For example, they were in exploration, they were in experimentation, or they were doing conclusions or discussion. So the machine we use deep neural networks with attention mechanism to predict in each group that is doing this lesson in which phase they are at any moment. We'll be doing this in other classes as well. In this book, Springer book, we have another one with physics classes in middle school, and seeing the different patterns of classes according to what the automatic transcription for the teacher said. So this is basically, in both cases, we train the computer using previous lessons and class and recording of the teacher, and where we have someone labeling every 15 seconds what a teacher is doing according to certain categories. And from these 100 or 200 lessons recorded that are labeled every 15 seconds, with that we train the computer. And the computer then will see a pattern, so discover a certain combination of words. And sometimes also we're also working with the audio directly, the kind of noise, the loudness or not of, and then the intonation of the teacher uh, also could help to decide what exactly is going on, in which phase is doing. We have been working also with other protocols like Couples Protocol for STEM lesson. Couples Protocol was proposed by Carl Wyman, Nobel Prize in Physics, that now also work in education. So how to label different moments in the STEM lesson. And this is very hard work to do this labeling, but so we are doing that, training the computer to learn to label these lessons every couple of seconds. And so you don't, in the future, not need to have someone listening or reading the transcription of the lesson. The computer will do it automatically for you. I mean, we will know in which phase, according to different protocols, the lesson is going on at this moment. So have profound implications in education now, and recommend you um, this publication. And if you're interested, you can write it to me. We can have other publications as well. But just in this book, we have 3 different publications. The other one is with the teaching to read and write to first graders using mobile apps, and also using some computational thinking behind. Well, so I'm just closing with this. I think why teach AI, computational thinking in our schools, I hope it will be clear, it's very important because the world is going in that direction. Um, Apps and different applications and software are listening to us, reading us, making predictions for us, and taking decisions for us. So we need to know how this thing is being done. For example, in the lesson, as a teacher, the computer is listening, analyzing the lesson, maybe suggesting you what to do, or maybe making decisions that saying, asking a question in the computer to a certain student or group of student, according to what you is listening, what you said, and the reactions of the student. So it's a profound implication. And secondly, how should we teach? I think we should have examples, more examples and more examples of important applications for all of us, depending on the age, like coloring books for primary school kids, first grade, second grade, third grade, and other ones like this in coronavirus or for middle school kids doing some graphs, and other more sophisticated like with mobility and using mask or not, and density of population, different conditions. It's very close to physics of collisions of objects, and this could be appropriate for high school. So we need to go into this, and we need to develop examples uh, and test those examples and make sure those examples help understanding AI and computational thinking. Well, thank you very much. Any questions? I think we have now question and answer. I hope to be there